Welcome to In 5 Minutes. The agenda of this clip is to understand how to implement a 1-bit full adder or 1-bit addition using CMOS transmission gates. And when we say full adder, that means we will have our inputs A, B and C in, and the outputs would be sum and C out respectively. Okay, let's get started. In the previous clips, we have seen that we have implemented sum in the equation of C out, and then we made the static circuit. We got something like sum equal to ABC plus the whole bracket A plus B plus C, the whole thing into C out bar. We found that using K-maps and then went ahead and implemented it in static style. Here we have to use transmission gates. So let's get started with that. Let's start with the sum. Sum is nothing but A XOR B XOR C in. Our propagate signal is nothing but A XOR B. So sum is nothing but P XOR C in. So basically sum is nothing but XOR implementation. If we can implement XOR using transmission gate, which we have already done in the previous clips, we are set and will get the value of our sum. Let's see what happens with carry. Now if you see properly, we have a propagate signal on basis of which we are predicting sum. So we should use the same propagate signal and see if we can find out our C out also. So let's see if we can do that. So if propagate is 1, we know that our C out is equal to C in. If propagate is 0, that means propagate bar is 1. That also means that if propagate is 0, my generate could be high or my K could be high. That is, generate is generate signal or K is kill signal. Both cannot be high because all three of them are mutually exclusive. Let's see what will happen when my propagate is equal to 0. When propagate is equal to low, it says that my A and B are not alternating. If they both would have been alternating, means one of them would have been a 1 and the other one would have been a 0, then my propagate signal would have been a high. But that's not the case. Propagate signal is low, so both are not alternating. This gives us a very important realization. That means A is equal to B. Now there can be two cases. Case 1, when A equal to B equal to 1, and case 2, when A equal to B equal to 0. If both of them are 1, we know that our C out is equal to 1, and if both of them are 0, we know that our C out is equal to 0. So can we easily say our C out when propagate is equal to 0 is nothing but the value A or B, because A is 0, C out is 0, A is 1, C out is 1, or we can also say because B is 1, C out is 1, B is 0, C out is 0. So we'll just implement this using transmission gate. Here also we will need a propagate signal, so we will need an XOR gate. We'll also need P bar signal, so we'll need an XNOR gate also, which we have already implemented previously, but we'll quickly implement again. And we'll keep this in our mind so that we can go ahead and achieve the functionality. So let's first quickly achieve XOR and XNOR. Let's start with XOR first. So this is XOR A, B, and output Y, 0, 0, 0, 1, 1, 0, and 1, 1. Output is going to be 0 here, 0 here, and 1 in the other two cases. So this is my XOR. We have already done this. If we make B of our select line, it says that if B is 0, 0 for a PMOS, then my output is equal to A. Because we are using a transmission gate, so I'm going to connect an NMOS in parallel. This will be B bar, opposite polarity. The other case is when B is equal to 1, my output is equal to A bar. So B is equal to 1. So for PMOS, that's going to be nothing but B bar. And this is going to be B. So if B is equal to 1, we just saw that our output is nothing but A bar. And this is going to be my output A XOR B, which is nothing but propagate in this case. I have implemented my propagate signal. Now I'm going to implement propagate bar signal, which is nothing but an XNOR. An XNOR, I'm going to just write it here again for XNOR. the truth table would be exactly opposite to XOR. So this will be 1, this will be 0, this will be 0, and this will be 1. So let's quickly go ahead and implement this. It's going to be exactly opposite to XOR. It says that when B is 0, my output is equal to A bar. So let's do that. When B is 0, A bar is going to come at my output. Let's connect an NMOS in parallel. We have done this in the previous clip. And this will have an input B bar. And when B is 1, the output is going to be A. When B is 1, that means for PMOS it's going to be a B bar. Output is A. B is 1, output is A. So this is nothing but my propagate bar. And we know that this A bar and B bar can easily be got from an inverter, which we can assume that A is the input, give it to an inverter, we get an A bar, and B is an input, give it to an inverter, and we get a B bar. So now we have propagate signal and propagate bar signal. Let's first go ahead and implement the sum. So very similar. Now this becomes P and this is Cin. So again, it's a 2-input XOR only. So we will have to just do a similar implementation for sum, where now we can say that, let's do the truth table so it's easier for you. So propagate is present, Cin is present, and both of them are XORed. So it's going to be same exactly the way I have written above. So sum is going to be nothing but 0, 1, 1, 0, and we'll implement it in exactly the same way like I have done above. So I'm not going to explain it right now. So this is my PMOSes. I'll connect in parallel the NMOSes. And if I'm making my Cin as a select signal, or we can also make a propagate signal as a select one, you can make any one of them. Let's make the propagate signal as a select signal. So if propagate signal is 0, my sum is equal to Cin. So let's call this as Cin. This as sum. Propagate 0 means to a PMOS, and this will become propagate bar. In other case, when propagate is 1, sum is equal to Cin bar. So this is Cin bar. Propagate 1. For a PMOS, it's going to be propagate bar, and this becomes propagate for an NMOS. So this is nothing but the sum implementation. Now let's quickly go ahead and implement the carry. So very simple. So for carry, we know that when my propagate is 1, I know that my Cout is equal to Cin. So this is my Cin, this is my Cout, connected in parallel with PMOS, which will have an opposite input, propagate bar. So when propagate is 1, Cout equal to Cin. We have seen that here. Now let's take the case when propagate is 0, that means propagate bar is 1. We know that our Cout is equal to A, or we can also say our Cout is equal to B. In this case, let's assume it as A. So let's quickly implement that as well. So this is going to be my NMOS connected in parallel to PMOS, which says that if propagate is 0, so PMOS will get a 0 and propagate bar is 1. So propagate is 0 at that point of time. We want our Cout to be equal to A, and this is nothing but my Cout overall. So this is my Cout. So this is nothing but my sum and Cout implementation in CMOS transmission gate style. It's a very straightforward thing. Hope you have followed. Stay tuned for further clips, and thank you very much.